Okay, so we just looked at a problem that spoke about the median weight of a boy whose age is between 0 and 36 months old. And it could be represented by this particular function, where t is the number of months, because t always represents time, and w is the weight, and it's actually in pounds. And the first question it wants to know is the rate of change with respect to time. Well, something we need to remember is this. Whenever they talk rate of change, they're talking about the derivative. Yeah, write that down. Whenever they talk about the rate of change, they're talking about the derivative. So, for this first part, we need to find the derivative of this particular function. So again, I'm assuming you remember the power rule. Okay, so and if you don't, go back and look at that previous section on us taking care of this. Or I should say the beginning of this, the different lecture that we did on differentiation techniques, part 1. There you go. Okay, so as I look at this and I take the derivative of it, I notice the derivative of the constant is 0. So I'm just going to write 0 as a placeholder. And then the derivative of 1.83t is just going to be, 1.83 minus, and so now the power comes down and we get to multiply by the number in front and reduce the power by 1. And the same thing with this next term. We bring the power down, multiply it by the coefficient, and reduce the power by 1. Good? Okay, so then this average, or I should say this rate of change, is looking like this function. And now this function is technically a second degree function with respect to time. So this would be the average rate of change of this particular function with respect to time. Are we in agreement? All right, good. So that was part A. Now, part B is asking us to find the weight of the boy at 9 months old. So, part B, find the weight of the boy at 9 months old. Now, here's the question. I technically have 2 equations to work with. I have the original one, and then I have this one that we found in part A. When they're asking us to find the weight, which one do we use? The original one or the derivative? Remember, all they're asking me to find is the weight. Good. I'm going to use the original one. Why? Because the original one talks about finding the weight. The one we found in part A is the rate of change of the weight. Part B isn't asking for the rate of change. It's asking for the actual weight at 9 months old. So we are going to find, using the original function, w of 9. And yes, I am going to write this out. And yes, I'm hoping that you guys get your calculators. And after you do the computation, that we'll all agree on our numbers. And if we don't agree, then maybe I've done some incorrect finger punching. So, that wouldn't be unusual, but that's okay. We're not perfect, and that's why we need to work these out together, right? All right, so this is what I got, and I am rounding it to 2 decimal places. I ended up with 24.18 pounds at 9 months old. Did you agree? And if you're not certain, get those calculators out. As a matter of fact, I'm going to get my calculator out and see if I actually need to adjust anything. So let's see. And we are going to... How's it going? Is your finger punching agreeing with mine? And Looks like this is what I got. I did a double check on my work. All right. Now, there is a part C. And part C would like us to find the average rate of change of the baby's weight at 9 months old. So part C is looking for the average rate of change of the weight at 9 months old. So, again, we have two formulas. We have the original one, and in part A we have the second one. We have the derivative. So, which one am I going to use? Am I going to use the original one, or do I use the derivative? Mind you, it's asking for the average rate of change. Yeah, they say average rate of change. They want you to use the derivative. And so, the average rate of change at 9 months old. So let's write this out. And yes, again, you more than likely have your calculators out still. I doubt that you've put them away. And that would be a good thing if you didn't. Why? Because, you know, we need to do some double checking on our work, right? All right, so I'm going to double check my work, and I'm going to see if I get the same answer again. Hopefully, you guys have already started your computation and are telling me if you're agreeing or not. Okay, so I have, to 2 decimal places, approximately 1.85. And you're like, well, what does that mean? That tells me this is 1.85 pounds per month. That is the rate at which the baby's weight is changing at 9 months old. It is changing at 1.85 pounds per month. Cool? Okay, so hang in there. I got another example. Okay, let's look at this next problem. This next problem is talking about the population of a city, and it grows from 900,000 to a size that they're calling capital P by this particular function. So, T is in years again, all right? So sometimes it's a good idea to write that down. T is in time. As I mentioned, it's always in time, and in this particular problem, it's in years. And P is the population. Now, they have a few parts to this question, so let's look at part A. Part A would like to know the growth rate. So again, they're looking for a rate, right? A rate of change. And in this particular case, they literally wrote down, take the derivative of P with respect to T. So, power rule, right? This 900,000, you take the derivative of a constant, you get a constant. And taking the derivative of this power, you bring the power down, multiply it by the coefficient, reduce by 1, which tells you, in this particular case, the growth rate will be 16,000 T. Agreed? All right. And then there's a part B. And part B says to please find the population after 10 years. Okay, so now you've got two functions to deal with. You've got the original one, and now you've got the 16,000 T, and I am just going to shorten this up and put P prime of T. Okay, because technically that's another way for me to write this. So which equation am I going to use? If I want to know the actual population after 10 years, what equation are you going to use? Yeah, you're going to use the original equation, because the original equation represents the population. Remember, this one is the rate of change. I don't care about the rate of change, I want the actual population. So, since I want the actual population after 10 years, I'm finding P of 10. We're going to plug it in. And I know you guys got your calculators out, so be my guest. I know what I got. What'd you guys get? Yep, I got 1,700,000 as the population. And it says the population of a certain city, so I'm just going to write people at the end here. Agreed? Okay. And now there's a part C. And part C says to find the growth rate at 10 years. So if we want the growth rate at 10 years, which equation will you use? The original one or the one in part A? Good, part A, because part A is representing the growth rate, and that's at 10 years. So when you plug that in, what do we get? Yeah, you get 160,000, right? Part D wants to actually know the meaning of this answer. Well, the meaning of this answer is saying that after 10 years, the population, the average rate of change over these 10 years, the average rate of change, the growth rate at 10 years is 160,000 people. Good? Okay, so hopefully this makes some sense to you, these two application problems. You guys have fun with this stuff, and I'll catch y'all.